All right, so let's go ahead and work through the process. I made a new step in the outline. We're doing an example of making something exact. So for us, we're gonna have to use that m sub v was equal to 2v and n sub x was equal to v. The two different things we can calculate to try and make this work are going to be m sub v minus n sub x over n, and n sub x minus n sub v over m. And you can't know ahead of time which one's going to work out. But for the first one, we've got m sub v is 2v, minus n sub x is v, and then n was that vx. So we've got 2v minus v is v divided by vx, or we just have 1 over x. The thing was that we wanted this quantity to only depend on x, which is true. So technically, if you were working on a problem, you could go ahead and stop, proceed with this one, because it's going to work. I'm going to calculate the other one though, just so you can see what it looks like when it doesn't work. So we've got n sub x was v minus m sub v was 2v, but then m was this v squared minus 32x. So v minus 2v gives us minus v, but that's divided by v squared minus 32x, which there's really no way to simplify that so that the x is gone. So this quantity cannot only depend on v, and so it doesn't meet that requirement for us to use it in our special factor. So instead, this is going to be the way to go. And we're going to use it to build an integrating factor. Mu equal to e to the integral of that thing we calculated, which looked very messy before, but it's actually just the integral of 1 over x dx. Integral of 1 over x is natural log x. And e and natural log cancel each other out, so this is actually just x. So like a lot of this section, even though the formula looked very messy in the steps, when you've got those generic m and n, when you're actually working through it, it gets a little bit easier. And then we multiply that throughout our ODE to obtain a new ODE to solve. So we take x times, where did my ODE go? There we go. X times all of this. So we've got x times v squared minus 32x dx plus x times vx dv is equal to x times 0. And that part on the right is always 0, so it's always just going to stay 0 when we do this. Simplifying that gives us xv squared minus 32x squared dx plus vx squared dv equal to 0. And from here we can go ahead and proceed with the regular steps for an exact equation. And they're all going to fit on one page, so I'm going to switch pages just so that you can see it all together at once. So we've got that xv squared. Where did it go? Xv squared minus 32x squared dx plus vx squared dv equal to 0. And we're solving this as an exact equation. If you wanted to, you could take the partial derivative of this with respect to v, and verify that it's the same as the partial derivative of that with respect to x. I'm not going to do it though, because you don't, as a rule, need to verify that the integrating factor worked. It's going to work. If you're worried you did it wrong though, you can check. But we think that f is going to be the integral of the m term, so that's xv squared minus 32x squared with respect to x. So we treat v like a constant. Integrating x gives us 1/2 x squared times v squared. And then 32 over 3 isn't anything special, so we're just going to have 32 over 3 x cubed when we integrate that x squared term. Since we were integrating with respect to x, there's some function in here that depends on v that we don't know what it is yet. But g is going to be whatever f is, minus the part that we did find already. And the derivative of that is going to take our n for the df dv, and then we take derivatives with respect to v of these terms right here. So derivative of this term is going to be 2 times a half, so just 1 x squared times v. And then derivative with respect to v of the second part is actually 0, because there is no v, and x is a constant as far as v is concerned. So we just have plus 0 there. So in this case, g prime of v equal to 0. So then g equal to the integral of g prime of v with respect to v is just going to give us the integral of 0, which is an unknown constant. Like I told you, when constants come out of this, we don't necessarily need to worry about them. They'll show up when we set it equal to a constant. I'm going to have this one here though and just show you how we combine them when we get our final answer. So, plugging in the unknown g back to our f, we have f is 1/2 x squared v squared minus 32 over 3x cubed plus that unknown constant. And then we set f equal to an unknown constant to make it a general solution. So we get 1/2 x squared v squared minus 32 over 3x cubed plus k is equal to c. Yeah. And I'm just going to write that as 1/2 x squared v squared minus 32 over 3x cubed equal to some c tilde, where c tilde is c minus k. Again, you don't need to keep track of like what your different constants are. You just need to make sure that there's only the one when you're done solving one of these types of problems. So combine constants to make sure there is only one unknown, because we'll only have one initial condition to help us get rid of it. So solving for v, we have 1/2 x squared v squared minus 32 over 3x cubed equal to c tilde. Gives us v squared is equal to c tilde plus 32 over 3x cubed, all of it divided by x squared times 2. Dividing by a half is multiplying by 2. Or v is equal to the square root of 2 over x squared times c tilde plus 32 over 3x cubed, which is not an easy equation, but it is an equation. And it looks like in our initial value problem, we were not given an initial condition. Sorry, it looks like in our problem, we were not given an initial condition. It's not an initial value problem. We were looking for the general solution, and so we have it. And we're done with this. So yeah, I'm gonna go ahead ahead and hit pause here, and then I have some tips and tricks to go over afterwards.